Okay, so hi everyone. Sorry for the chit chat in Portuguese. We haven't seen each other for a while, so it's have to keep up with the news. Um, Today um, we are having Ivan Struchiner from USP and some of his co-authors also present here. Ivan is going to tell us about Lie groupoids and singular Riemannian foliations. Let me remind you that you can subscribe to our mailing list by sending the word webinar to the email to be found on the chat. And you can join our WhatsApp group for announcements, strictly announcements relevant to geometry and the seminar by following the link also provided. You can check our calendar at our webpage, which by the way is complete for this year. So our calendar is already complete for 2022, as well as check on our recorded talks on our YouTube channel, which you may or may not like, we don't mind, which you may or may not subscribe, we don't mind, but interact with the content, that's what's important. So without further ado, Ivan, let's have a go. Can you do it in 50 minutes and then 5 more minutes questions?
Sure, just stop me when the time arrives.
I don't want to be rude. I have a
No,
reputation
please let me
for
know. I mean, please tell
gentlemen
me,
like,
but
hey,
please tell
yeah.
me when the time is finished.
Yeah, but let's do it. Let's do it till 3, and then we take a few more questions. Basically.
Perfect, perfect.
All right, off you go.
So thank you very much for the invitation, and I'm going to talk about Lie groupoids and singular Riemannian foliations, which is joint work with Marcos Alexandrino, Marcelo, Inagaki, and Mateus and Melo, all at USP at this moment. Um but I have to make a disclaimer before I start. So when I started, so I decided to talk about this topic because I think it's maybe one of the less exotic things that I do for this audience, maybe. So more differential geometric things. And apparently I thought the same thing 1 year ago when I gave the talk to you guys. So when I started preparing, I noticed that I had given a talk with maybe, if not exactly the same title, something very similar in a very similar abstract. So what I decided to do is to keep the topic, but try to give a different point of view of the same thing, and well, try to tell you maybe some new things that have been going on, and see what happens. Probably none of you remember my other talk, so you can also check it out on YouTube on the channel. But I'll try not to repeat myself too
I
much.
think I remember you giving the same title since I came back to Brazil, so at least a decade. But that's cool. It's always
Well,
interesting.
that's not possible. The same title a decade ago is not possible because this work is maybe 1 year or 2, 1 year and a
There
half
you go.
old or something.
There you go.
So, okay, so let's go. So let me start with some motivation, and so I'm interested in these singular foliations, which are of metric type. So they are singular Riemannian foliations, and I'll tell you what they are soon. And what I want to understand is the dynamics of this foliation. So foliation is a partition of a manifold into submanifolds. And these submanifolds can have a very complicated behavior. So that they can wrap, like you can have like a central manifold, and then the other manifolds can wrap around it. They can get close, they can get far. They can, there's several sorts of dynamics that can happen around these leaves. And I'm quite interested in understanding what's going on. For the case of singular Riemannian foliations. So this is the motivation. This is where I'm aiming at arriving. And so the question is like, how do other leaves twirl around a central submanifold, say B, which could be a leaf, or could be the closure of a leaf, or could be a union of leaves, or something like that. And also what the geometry of this quotient, which is very singular spaces. So like, what is the transverse geometry to the foliation? The geometry which is transverse to the foliation. So this is where I'm aiming, and here's my plan. So I want to start with the case of regular foliation. So I want to tell you how to understand these problems, this dynamical behavior of the leaves in the regular case. And this will lead us to understand holonomy, a bit of the holonomy group. And again, I should warn you guys here that there are two, the word holonomy here appears in two different senses. So there's the holonomy of a foliation and the holonomy of a connection. And I'll try to make it clear from context which one I'm talking about. But now I'm talking about the holonomy of the foliation. I'll define it very soon. So I'll discuss the regular case for quite some time. Then I'll tell you what the singular Riemannian foliation is, and the model for the singular Riemannian foliation around a leaf, or the closure of a leaf, or a regular stratum. And finally, I'll tell you, instead of telling you what the linear holonomy group or the singular foliation is, which is somehow what the best we can have to describe the so far, right? Is the best we get to describe this dynamics. I'll tell you what the algebroid is, and this is how the talk will differ from the next one. So this, maybe I just put this. Great, I got rid of it. So I'll try to show you how the construction can be thought of as a foliated version of the Ambrose-Singer holonomy reduction theorem. And this was, I guess, specially thought for the gauge theory people here. I remember Enrique asked me this quite a lot last time I gave the talk. So I'll try to show you how this goes. So that's the plan, and let's get started. So a regular foliation on a manifold M, is a partition of M into, say, k-dimensional submanifolds, all of the same dimension. So that's where the word regular comes from. So they're all of the same dimension, which locally looks like Rk times Rn minus k. So locally, it's really just the partition by flat plane k planes in Rn, and equivalently, you can say that it's an involutive constant rank distribution on the manifold M. So when you have a foliation, you look locally, and it locally looks like some Rn. But you see, I tried to put some colors in the leaves here, and so you have some kind of this black leaf, which is a central leaf here, for where I'm trying to understand what's going on. And the leaves nearby can maybe, when they go around the border, it's not really a border, but the border of my picture, they can come back and reach the other side. And I'll give an explicit example on the Mobius band soon. So you see that this foliation is, these leaves are wrapping around the central leaf. And this is the kind of dynamical situation that's going on, which I want to understand. And this is controlled by what is called holonomy. So the holonomy of let's first describe what the holonomy of a path is. So suppose you have, say, a path inside the leaf. So alpha is a path inside the leaf. And you fix some transversals. Let's call it T0, T1, T2, and so on. So some submanifolds, some slices which were transverse to the foliation, some small transversals to the foliation. And since your path locally looks like a product, your foliation locally looks like a product, you can perturb, you can horizontally translate your path to nearby leaves to get a map which goes from one transversal to the next one, as long as you're inside one of these foliated charts, right? Now, if you compose all of these, so you get a map from here to here, and then a map from here to here, and then so on, and then you might, if you have, say, you had a loop, you might come back to the same transversal, and you got a map from the transversal to the transversal. Let's call this map, say phi alpha. So in principle, this is a map from a transversal at alpha of 0 to a transversal at alpha of 1. And it's the germ at alpha of 0 of phi alpha does not depend on any choices. It's canonical. Let's try it like this. It's canonical. It's canonical. So it does not depend on any of the choices. So the choice of charts or the choice of transversals and so on. And we say that alpha is has the same holonomy as beta. So two paths which start and end at the same point. So have the same holonomy if and only if the germ of phi alpha at alpha of 0 is equal to the germ of phi beta. Well, at alpha of 0, which is the same thing as beta of 0. So if they induce the same holonomy transformation on this transversal. So let me give an explicit example. Oh, and by the way, so we can talk about the holonomy group of a leaf at a point, which is, you look at the holonomy classes of loops at that point, loops inside the leaf. So these will be transformations which go from the transversal to itself. The holonomy transformations will go from the transversal to itself. And these form a group by concatenation of paths. So you get a nice group. This holonomy class of determined by a path actually only depends on its homotopy class. So you get a nice product by concatenation, which is if you take the holonomy classes, it's associative, it has an inverse, and also so you get really a group. So you get the holonomy group at a point. Okay. So here's an example. This is the Mobius band, and let's draw a transversal, say here. And alpha for me is this red path, which is also a leaf. So it's the path which starts here, and maybe I should draw the path in black. So it starts here and it goes around this way once. So this is alpha. And so if you perturb alpha a little bit, you'll get this path, which starts here and ends here, right? So it maps this point to this point, and it maps this point to this point, and so on. And if you go around twice, you get the identity, right? So if you go around twice, you'll come back to this point. So the holonomy transformation on this transversal is Z2. And since alpha generates all paths which go around this loop, this is really the holonomy group. The holonomy group here. So holonomy group of L at X is just Z mod 2. So it's the only difference is if you do alpha once or if you do alpha twice. Any questions so far? Is this clear?
I have a question.
Sure.
If these examples, they are with the foliation is obtained with curves, but if the leaves are surface or something like that, how do we visualize?
No, it's the same thing. I mean, you're going to take a path inside. So maybe look at not what I'm writing, but at the video. So you'll take a path inside the surface, which is a closed path, a loop, and the nearby leaves are also surfaces, but locally it looks like a product, which is just R2 times your ambient, Rn minus 2, right? So you can parallel translate these curves and you'll get a small curve nearby, and then you concatenate with another small curve and so on. And at some point you'll come back to the transversal. And it's exactly the same picture. I mean, it doesn't matter that my drawing is one-dimensional, right? So what you get in that case is you have a map from pi1 of the leaf, well, with base point x, to the holonomy group of L. So it really
Not
only
quite, right? It's the loop group of the leaf, right?
It's the loop group, but the holonomy class only depends on the homotopy class of the path, right?
Are we
so
sure?
Homotopic paths will have the same the same holonomy.
Only if you're flat. If your foliation is endowed with a flat connection along the leaves, I think that's true.
I think
Yeah,
that's
I have the same impression.
I think that's always true. But anyways, so but anyways, it's true because you do get a well-determined. No, what I'm saying is definitely true. I mean, what I'm saying is definitely true. You get the holonomy group is a quotient of the fundamental group, and I mean, if you want to, this is not really the holonomy of a connection, right? I mean, so that's, I think that's where the confusion is coming from. But if you want, and we'll talk about this very soon, but if you want to think about a connection, so a linear approximation to your foliation, just to make things a little bit simpler, you can think about the normal bundle with the bot connection. It's something I'll tell you soon. And the holonomy of this connection, and this is always a flat connection. So
Cool.
So the reason this thing works is because you're really looking at these these things which are defined in terms of the very local nature of the foliation, which is flat. And that's why it works.
So you have a sort of locally flat setup. Fine, you're doing something infinitesimal, but as I think you're about to say, there's this bot connection sort of globally, which is flat, sort of along the leaves, and that'll be the holonomy of this connection, right? So
it will not.
Yeah,
it will not. The differential of the holonomy transformation, right? I mean, the holonomy transformation is not a linear thing. It's not a linear phenomenon, but it's differential, which is linear, which is a map from the transverse at one point to the transverse at the same point. So the normal space at a point to the normal space itself. That is a linear map, right? The differential of the holonomy transformation. And that is the holonomy of the bot connection. So the linearization of the holonomy is the holonomy of a connection. They're two different. I mean, it's not the same thing, but.
You can think as a connection, not in the sense of a linear connection, but a connection on fiber bundles, right? If you take the quotient, then you have a fiber bundle, and it is a connection in the sense that you can lift the curves.
Yeah, if the quotient was smooth, you could do something like that.
Yes.
I mean, morally, you can think of it like that.
Yeah, just for the sake of intuition, I mean.
Yeah.
Okay, let's move on. We can come back to this at the questions.
Sure. But let me just say something. That in fact, there is something to be proven here, right? That this only depends on the homotopy class of the map is something to be proven, and you can find it in any book on foliations. But we can also discuss it. But okay. So if instead of taking loops, you take just paths, then you get what is called the holonomy groupoid of the foliation. And so you take holonomy classes of paths, and you can multiply two paths if one of them finishes where the other one starts. And this is the holonomy groupoid. Since I won't get too much into the theory of groupoids, I'm not even going to define groupoid. I just wanted to mention that this is the holonomy groupoid of the foliation. And this is the object which controls this dynamical behavior around the leaf. So I made a slide written why holonomy groupoid. So the first thing is that it's canonically associated to your foliation. And then the second thing is that it is a model for the transverse geometry of F. So you can look at the Morita class of this groupoid, and you can really model what's happening in the transverse directions. And you can use this to construct invariants of your foliation. So for example, if you have a groupoid, you can consider the classifying space of your groupoid. And if you look at the cohomology of the classifying space of your groupoid, it will be giving you certain characteristic classes which are invariants of your foliation. So this is a way to get invariants of your foliation. And also it's useful to, I mean, you don't need it. The theorem I'm going to state about local models is older than groupoids, but it's useful in finding local models or linearization of your foliation. So this is something which will be important in this talk. And I'll keep myself only to the foliation and not at what's happening at the level of the groupoid. So let me tell you what the local model is for F. So say you start, now I'll tell you what the bot connection is also. So say you start with a leaf, you start with a foliation F and you have a leaf. Then you can construct a linear foliation on so a new foliation if you want, on the normal bundle to the leaf. So this is just this quotient bundle, the normal bundle to the leaf. And it's built from the bot connection. So the bot connection is a connection which takes a vector field on L, a section of the normal bundle of L, produces you a section of the normal bundle of L. And it's just defined by so nabla x of, say, V mod TL is just the bracket of x and V mod TL. So you show that this is well defined, and this is a flat connection. So this is a flat connection. It's called the bot connection. So it's a flat connection. There's several ways you can think about it now. So it induces a horizontal distribution, which is involutive on the normal bundle of L, and the leaves of this horizontal distribution is your linearized foliation. Or the way I want to state it here is you can take a foliation called F-lin, which is given so let's say this has linear leaves, so L-lin of V is so this leaf is just parallel translation by alpha of V for all alpha in L. Alpha of 0 is equal to pi of so the same starting point to the base point of V. And so you parallel translate this guy in all possible directions, and you get a leaf, and this gives you a foliation which is linear. So this foliation is actually quite nice. So maybe let me add a page here just to have some space and tell you this. So add a page here. Okay. So this foliation is actually quite nice. You have a very explicit model of what is going on this foliation. So if you want, you can think about the normal bundle of L as an associated bundle in the following way. So you have what's called the holonomy cover of your leaf. So this is the cover of the leaf, which corresponds to the subgroup of pi1, which is the kernel of the map, which goes to the holonomy group. So there's a cover which corresponds to the holonomy group in this sense. And so you take the holonomy cover of the leaf, you multiply it by the normal space at a point. So here the normal space at the point is just TXM times modulo TXL. And you quotient it out by the linear action of the holonomy group at L. So here, this action is, well, here it's just really because the holonomy group acts on this cover. That's why it's the holonomy cover. But also, and this guy here, it's really a linear action. It's the differential of the action by the holonomy transformations. So it gives you a linear action on this guy. And then the leaves here, so the linear leaf at V is just, well, you can look at L tilde times the orbit of V, so whole XL times V, the class of V, modulo X. Well, so what this means is on the fibers, you just have the action of this linear representation, and then you just translate these tubes by using the paths you want. I mean, this is really what's going on. So it's really a linear foliation in this sense. So in any case, this is like a very explicit model of the foliation somehow. Okay. So there's a theorem which is quite nice. It's called the Rib Stability Theorem, and it tells you that if L is compact and the holonomy group of the leaf L is finite, then your original foliation is locally foliated diffeomorphic, so it's locally isomorphic to the linearized foliation, to the linear foliation. And the linear foliation is really given by, so the holonomy of the linear foliation is really be given by the holonomy of our connection, right? So holonomy of the bot connection. But in general, these two foliations are not isomorphic, right? So there is a map which relates them, but they're generally not isomorphic. In any case, this case is very nice because the dynamics which I was interested in, so this what's happening transverse to the leaf, is just given by this linear representation of this finite group on this vector space, and this is describing the whole situation. Questions until here? Nope. Good. Okay. So let me tell you. Let me stick to the regular case and tell you what happens when you have a Riemannian metric around. So in the case of a regular Riemannian foliation, So F is a foliation on a Riemannian manifold, and now you can identify the normal bundle of L with its orthogonal complement, the orthogonal complement of TL, and being a Riemannian foliation is just saying that the holonomy groups act through isometries. So this linear action of the holonomy group on the normal spaces are through isometries. Okay, and in this case, you can prove that as long as you have just a second, Henrique, but you can prove that as long as you have if your metric is complete, which is an assumption I'm going to make throughout the talk, so if I forget to say it, our metric is complete. As long as your leaf is closed, your foliation is linearizable around the leaf. So yeah, Henrique, ask your question.
Right. So just to be clear, so if you're still defining holonomy as produced by parallel transport here?
Sure. Yeah.
Yeah. So parallel transport requires a connection, right?
Well, I mean, so you can do both things, right? So since I'm looking here at the linear action of this on this, you can think about it as being the linearization of the action you had where you defined holonomy the way I defined it in the beginning, where I did not use a connection. Or you can think about it as in terms of the bot connection, and then the condition is just that the bot connection is compatible with the metric that you have on the canonical metric on the normal bundle of L, the metric induced by the metric you have on N.
So in that case, can you please just recall how you defined it in the beginning? So just in broad words.
How I defined the
holonomy action. Yeah, because I think I might have. There's something I might have missed.
So you have your leaves, and then you have a path inside the leaf, and then you perturb it slightly because locally your foliation looks like a product, so you can perturb it slightly, and then you slide from one transversal to the other using this path that you perturbed. Then if you do this again, you will slide to a new transversal, and then do this again, you will slide to a new transversal. And if your curve was a closed path, eventually you'll come back and you will slide back to this transversal.
Right. It's some kind of monodromy which extends.
It is a monodromy, yeah.
Right. Right. Okay. Okay. I understand. Then it's kind of apparent that if your path is if your loop is contractible, then its holonomy will be trivial, right?
Because yes, because it will be inside one of these. Well, if you have a small loop, let's say if you have a small loop, it will be trivial, right?
But it could be not small and still contractible.
It will be trivial.
And well, then
that you have to prove. What?
Right. But if you proving that means proving that the pi one.
Yeah, it's equivalent to what I had said before.
Yeah, that's right. Yeah. Okay. Are you going to prove it?
No.
Okay, never mind. It's an exercise for me. Thanks.
No. Okay.
Okay.
But anyways, so this is, I guess, this result that regular Riemannian foliations are linearizable around a closed leaf should not be so surprising, because now your holonomy transformations act by isometries, and isometries are totally determined by their one jets. So they're totally determined by their differential at the point. So essentially, the linear holonomy should determine the whole holonomy, the entire holonomy of the path. And so your foliation should be governed. This dynamics is governed by a linear dynamics, and so your foliation should be linear in some sense. And this is what this is the precise statement: is that your foliation is isomorphic to the linear foliation you get by the bot connection. So, but it should not be so surprising. Okay. So this is the let's say the conclusion of what I wanted to say in the regular case. So if you have a Riemannian foliation, a complete Riemannian Riemannian foliation on a complete Riemannian manifold and a closed leaf, then locally your foliation is isomorphic to the linear foliation, and you can describe its dynamical behavior, its holonomy, in a very simple way. So the transverse geometry is just given by the holonomy group of the bot connection acting on this vector space, if you want. Or if you want, you can describe the foliation by using the bot connection. Both things very quickly. So you have complete control of what's going on. So this finishes the regular case, and now I'm going to start telling you about singular Riemannian foliations. So I think it's a good point to ask if you still want to ask questions about the regular case.
In the regular case, if I take the quotient of the manifold by the foliations, is the quotient orbifold?
Not in general, not necessarily. If you're in the Riemannian case,
because I remember in the case when you have a group, a compact group acting with some hypothesis, I remember that the quotient usually is orbifold. So I'm trying to make an analogy.
You need to have. So let's see. I think that if you're in the case of a Riemannian foliation, the quotient is orbifold. Is that right, Marcos, Mateus? But in general, for foliations, the quotient can be very badly behaved. So, I mean, just think about, say, the Kronecker foliation on the torus, given by
a dense warp, yeah.
Yeah. So I mean, the quotient can be very bad.
Yeah, certainly not orbifold. Yes, of course.
So if the foliation is closed, then it is orbifold. That's what Mateus answered. Okay. So in general, it is not orbifold. But I mean, you see, this is also somehow controlled by the holonomy groups, right? I mean, this is really what the holonomy group is telling you, right? So if you want an orbifold, it should be. I mean, the transverse geometry should be something like a vector space quotient by a finite group, right? And the group which is acting on this transverse space in giving you the structure on your quotient is the holonomy group. So it will be orbifold if the holonomy groups are finite.
Yes. Okay.
And actually it will be, say, possibly non-Hausdorff manifold, or I mean, let's say manifold, if the holonomy groups are trivial, right? So let me put it the other way. If the quotient is a manifold, then the holonomy groups are trivial. So really, these holonomy groups are telling you this behavior of the quotient space or the transverse geometry. Okay, so let's move on, and I'll tell you quickly about singular Riemannian foliations. So here the word singular means that the dimension of the leaves can change from one point to the other. So not all leaves have the same dimension. So if you start with a manifold with a Riemannian metric, and so you have a partition of M into submanifolds, which may vary in dimension, but you ask for two things. The first thing is that this partition should be smooth, in the sense that if you have a vector which is tangent to one leaf, you can extend it to a vector field which is tangent to all leaves. So at least locally you can do this. Extend it to a vector field which is tangent to all leaves. And it's a Riemannian foliation if a geodesic which is perpendicular to one leaf is perpendicular to all the leaves that it meets. So this is what a singular Riemannian foliation is. And what I want to understand is, what is this dynamical behavior of these singular Riemannian foliations? Okay, so if you start with a singular Riemannian foliation, then you can linearize it in the following way. So I'm going to linearize it around a closed regular submanifold. So regular means that the foliation F intersected with B, which I will usually denote by FB, is a regular foliation. So it could be, for example, the closure of a leaf, and I really want it to be closed because of things which will come afterwards, but the linearization itself doesn't need it to be closed. Mm-hmm. And look at the normal bundle to this leaf. So a linear foliation is always a foliation on a vector bundle, which has some kind of linear behavior. You can actually make this precise. So what you want is that the distribution is a linear distribution in the sense, so somehow the tangent distributes. So if you look at vectors which are tangent to one leaf and vector which is tangent to another leaf, but over the same point, then you have the differential of addition. This will give you a vector which is tangent to another leaf, or something like that. But anyways, it's not really important what it means for foliation to be linear. But we will get a foliation on this vector bundle. And to do it, I mean, you can start by identifying your vector bundle with a tubular neighborhood of your manifold B. With that, you get a foliation which is not linear on this vector bundle. I'm going to call it D just to not write normal to B all the time. So you get this foliation on this vector bundle, and it's this foliation which you linearize. So how do you linearize a foliation? Well, you look at you can start with a vector which is say a vector field which is tangent to the leaves of the foliation. Let me denote it like this: a vector field which is tangent to the leaf. Then you can construct a linear vector field associated to it, which computed at a point V is just the differential at V of multiplication by 1 over lambda of psi at lambda V. So you take homothetic transformations of psi lambda V, and then you take the limit when lambda goes to 0 of this. And this will give you a linear vector field on E, on the total space of V. And you take
what is M?
M is multiplication by 1 over lambda. So MA is a map from E to E, which takes V to AV. Right? And then you take the foliation, which is generated by flows of the vectors psi L, the vector fields psi L. These are. This is the linearized foliation on. So this is what I mean by the linearized foliation. So it's generated by linear vector fields on your vector bundle. Okay. So you can construct this foliation. So this is a theorem that I'm stating here. Actually, so this slide is to state this theorem. This is a theorem which is in our paper with Marcos, Marcelo, and Mateus. But I should say that this is a theorem of Marcelo Inagaki, or maybe Marcelo and Marcos. When we started this project, they already had proven this theorem. It's in Marcelo's thesis, so it's really, I mean, it should be only their names on this. Okay, so the theorem says the following: you can, for this linearized foliation, you can describe it in terms of certain local data, and this local data is so you have this foliation on the vector bundle, and you can look at the intersection with each fiber of the foliation, F-lin, or actually of Fe. It's the foliation. So the foliation you started with intersected with the fiber, and this will be a foliation on this vector space, on this fiber, and it has a maximal connected group of isometries, which is a Lie group. And this is something you have to prove. You have to prove that it's a Lie group, and they prove it. So this is something that Marcelo, or I guess that Marcos had proven before in another paper of his. But so this is a Lie group. And the other piece of data is that you have a connection which plays the role of the bot connection. So it's something you define canonically out of your foliation, and it's a F partial, so a foliated connection on this vector bundle E, which is compatible with the metric on E. And using these two pieces of data, you can describe the linearized foliation as being obtained by parallel translation of the orbits of this group acting linearly by isometries on the fiber. So you see that this has the kind of flavor of the bot foliation of the linear foliation on the normal bundle when you have a bot connection, right? So it's really, you have this a representation of a linear representation on the fiber, and then you just use your connection to parallel translate it. So to get the leaves. And so this is what's going on here. And in fact, if you apply precisely this construction to the case where of a regular foliation, you recover the local model for a regular foliation that I told you guys about. Okay, so this is the data, and so here I'm actually just recasting the data, but from say almost the same point of view. I said infinitesimal point of view, but just because I'm using the Holonomy Lie algebra of this connection instead of the Holonomy group of this connection. But maybe just to let's say that this is kind of a summary. So you have a regular foliation on B. You have a vector bundle over B, which is in the case of a foliation, this is just a normal bundle of B inside of M. And then you have an F partial connection, so a connection which is only defined. You can derivate sections of V, but only along vector fields which are tangent to the leaves of this foliation on B. And you have a bundle of Lie algebras, which are just the Lie algebras of these groups K0B, which is a bundle of Lie algebras. And it happens that the holonomy, and now it's really the connection holonomy, so the holonomy Lie algebra of this connection is a subalgebra of the fiber of this bundle of Lie algebras, and the fiber is a subalgebra of the general linear Lie algebra, so matrices or endomorphisms of this vector space, EB. So this is the data that you get from a Riemannian foliation if you linearize it. And what I want to tell you a bit in the last 10 minutes that I have is how to, from this data, how to construct the holonomy Lie algebroid. So the Lie algebroid, which should be thought of as the tangent to the foliation, the linear foliation. So the thing which, when you integrate, gives you the holonomy groupoid of this linear foliation. And if you're more interested in the holonomy groupoid, which is what I talked about the whole talk, then I gave this construction explicitly 1 year ago in this seminar, and you can go check it out on the website of the seminar. So the talk is there on YouTube. And that's why I want to tell you what the Lie algebroid is now. So I'm going to describe the Lie algebroid of the groupoid I described a year ago, but I think it's also a very nice construction. Are there any questions? Of course, I'll tell you what an algebroid is, and I'll tell you the words I said here, which I haven't defined it. But are there questions here? If not, okay.
I think we're fine.
So from this data, we will construct a Lie algebroid. I'll denote it by A, which is a Lie algebroid over this base manifold B. And it comes with a representation on E, so that if you take the action of A on E, it has Lie algebroids have leaves, and these leaves are precisely the leaves of this linear foliation. And it's really so canonically defined and so intrinsically connected to the foliation that it really should be thought of as the tangent space to the foliation. So the tangent algebroid of the foliation. Just to make this clear, if you have really a regular foliation, then you can look at the tangent bundle of the foliation, which is just a distribution which is tangent to the leaves. And this is something which sits inside TM, and it is a Lie algebroid, and it's called the tangent algebroid of this foliation. So it's, in this sense, something very canonically associated to the foliation. It's the infinitesimal object associated to the holonomy groupoids. And this guy has precisely the same role as this one in the regular case. So this is what I want to tell you how to construct. And instead of giving you a, say, a straightforward direct construction, which I will give, but I want to tell you how this construction can be thought of as a foliated version of the Ambrose-Singer holonomy reduction theorem. So let me remind you what the holonomy reduction theorem is. So the classical reduction theorem, it tells you the following. So you can state it either on principal. I mean, I prefer it on principal bundles, but since I was talking about vector bundles, let's state it on vector bundles. And then here I have the statement for the frame bundle of this vector bundle, but you could state it for principal bundles. But it tells you the following. Suppose you have a vector bundle, and you have a connection on this vector bundle, and you have the holonomy groups of this, the holonomy group of this connection. Then you can take an atlas of your vector bundle, which is compatible in the sense that the changes of atlases lie in this holonomy group instead of lying in this bigger group. So you have a reduction of the structure group of your vector bundle to the holonomy guy. And I guess that's the statement in terms of vector bundles. In terms of principal bundles, so I'll state it for the frame bundle of V, it's just saying that you have a principal sub-bundle whose structure group is the holonomy group of Nabla, and moreover, this your original connection restricts to a connection on this bundle. So if you restrict your original connection form to this bundle, you get a connection for this bundle. So I guess this is the classical Ambrose-Singer reduction theorem. It's a very nice theorem, right? So, I mean, for example, if you want to prove things like, say, being a Riemannian manifold is a Kähler manifold if and only if you have if and only if the Levi-Civita connection has holonomy group inside of UN. This is precisely what you're doing, right? You'll take a reduction of the orthogonal frame bundle to the frame bundle, to the UN frame bundle that you get by reducing to the holonomy reduction and then extending it to the UN bundle. So I mean, this is what you use to prove these kind of statements where you're trying to understand tensors which are compatible with more than one structure. Okay. So here's a sketch of the proof of this classical holonomy reduction theorem, Ambrose-Singer holonomy reduction theorem. So if you take your connection, which you can view it as a connection form on the frame bundle or a horizontal distribution, and you can identify the tangent space at a point of the frame bundle of V with its horizontal space plus its vertical space, right, using the connection. And the vertical space is canonically just the Lie algebra of the structure group, which is GLR. Now you get a distribution on the frame bundle which at the point P is just, well, the whole horizontal space plus the holonomy Lie algebra at P, right? So this is a Lie subalgebra of this, and then you take it at under this identification, you take this vertical direction. In general, if you forget this, if you take only the horizontal space, it will not give you a involutive distribution. And the failure of it being involutive is precisely the curvature of your connection. But if you put this, then the Ambrose-Singer holonomy theorem will tell you that this distribution is involutive, right? So you can generate the holonomy by taking the curvatures of pairs of vectors. And so this is involutive, and if you take a leaf of it, it will be the reduction that you're looking for. So this is I mean, of course, there are details to check, but this is the sketch of the proof of the classical Ambrose-Singer holonomy reduction theorem. Okay, perfect. So the remark is that if you look at this distribution that I just constructed and you mod out by GLR, you get a vector bundle over B, which sits inside this quotient, and it's a Lie subalgebroid. So at this point, I cannot push away, and I have to tell you what an algebroid is. So here's a very quick definition of a Lie algebroid. So a Lie algebroid is a vector bundle together with a Lie bracket on the sections of this vector bundle, and a bundle map called the anchor, which goes from A to Tm. such that the following Leibniz identity holds. So the bracket is not the infinity of M linear, but it satisfies the Leibniz rule. It satisfies the derivation rule, just like the Lie bracket on Tm satisfies. So here are some examples. A Lie algebroid over a point is just a Lie algebra. The tangent bundle to a manifold is with its usual bracket and with rho being the identity in M is a Lie algebroid. The tangent bundle to a foliation with rho being the inclusion, so TF includes into TM, is a Lie algebroid. And then there's this Lie algebroid, which I'll describe now, which is the one which appears in the Ambrose-Singer holonomy reduction theorem. So I think I have 2 minutes, and I'll probably go past only 2 minutes if that's okay with you, Enrique.
It's cool.
Okay, cool. So here, this is called the general linear algebroid of a vector bundle E. And it's the, if you want, as a vector bundle, it's just the tangent bundle to the frame bundle of E modulo the GLR. So its sections are just invariant vector fields on this principal bundle. And this gives you a Lie bracket on sections because the Lie bracket of invariant sections are invariant again. Okay. Of invariant vector fields are invariant again. So this is what's written there. But the nice thing is that you can identify these invariant vector fields on the frame bundle of E with things which are called derivations of the vector bundle E. So a derivation of the vector bundle E is just a map from the sections of V to the sections of V, which satisfies the Leibniz rule, so which is a degree 1 derivation, in the sense that D of if you have, it's not the infinity of M linear, but the failure is controlled by a vector field on M, which you associate to each D, which is called the symbol of the derivation. So I wrote how to explicitly go from here to here. I wrote it here, but it's not really important. So really, we have derivations of V, and if you try to think about this as if you want a nice exercise, and it's really an exercise. It's a good exercise for a course in differential geometry. This as a vector bundle, GLE sits inside an exact sequence of vector bundles. So this is the anchor, which is really just giving the symbol of the derivation on sections. And this is just this just endomorphisms of V, right? Endomorphisms of V. So if you look at the derivations which have 0 symbol, they are C infinity of M linear, so they are endomorphisms of V. So that's it. And the splittings of this exact sequence are in one-to-one correspondence. So let me write a sigma here. They're in one-to-one correspondence with connections on E. So how does this go? So if you have a splitting sigma, you can define a connection nabla sigma just by setting. Let's do the following. So if you have a connection nabla, let me do the other direction, and then I'll. So if you have a connection nabla, you can induce a nabla applied to X is just nabla X. So this is your derivation, and it has symbol X. And then I'll tell you that this is a one-to-one correspondence, so write the other direction. So how you get from a splitting, you get a connection. In any ways, so given a connection on the vector bundle E, you can redescribe this vector bundle, so the general linear algebra of V, as this vector bundle direct stub with this vector bundle. And you can write what the bracket is on this using this identification. And if you do so, you get, so on a pair X phi, where X is a vector field and phi is an endomorphism with wipe psi, you get the bracket of vector fields. Then you get the curvature of the connection. You get the action of nabla X on psi by the induced connection on the vector bundle of endomorphisms, and you get the commutator bracket of endomorphisms. I don't really care about this formula right now, but it's what you have to use to show the following. The restatement of the Ambrose-Singer theorem is that a connection on E with holonomy group inside a certain Lie algebra K is the same thing as a transitive Lie subalgebroid of this general linear algebroid, whose kernel of the anchor is K, and plus a splitting of this exact sequence, which is the connection. So saying that the kernel is K is what's telling you that the holonomy group will lie inside of K. And this is a one-to-one correspondence. So this is say a restatement of the Ambrose-Singer holonomy theorem in terms of the algebroids, and then you can do the foliated version of this, which is what we needed. So you can construct the general linear foliated. So you have a vector bundle over B, and B has a foliation, or over M, and M has a foliation. So you can look at derivations whose symbols are tangent to the foliation. Then you get a Lie algebroid which fits into an exact sequence. Splittings correspond to F partial connections, and if you have a foliation with a connection and the bundle of Lie algebras such that the holonomy Lie algebras all sit inside this bundle of Lie algebras, you get a reduction of the of this Lie algebroid to this one plus a splitting, and this is the in one-to-one correspondence in some sense. So the idea is that you want to have a reduction, but you only have a foliated connection. So these holonomy Lie algebras could change dimension, and you couldn't really reduce it. But if you put them all inside a bundle of Lie algebras, so something which has constant rank, then you can do this. And I'm way past over time, so I'll stop here. And thank you.
All right, thank you. Have you got any questions for Ivan?
I'm sorry I ran a lot at the end.
If there are no questions, then I have a question actually.
Okay.
So can you use this technology to learn something about the holonomy of the leaf space, right? So you look at the holonomy of Marcos, is your microphone on?
I think so. Sorry.
Are you going to ask a question?
When I let that
Okay.
open, okay.
In any case, if people have questions, just raise the little hand thing. So I was wondering, can you say so, by knowing the holonomy of the total space of the foliation, can we does this go over in some respect? Can you control how this goes over to the leaf space? Right? Because that's kind of in the spirit of Ambrose Singer in a way.
Yeah, I don't know. So I mean, I think so. Let me say maybe two comments which I should have made, or one comment which I should have made before, and then I'll try to answer a question. You see, we still do not know what the holonomy groupoid of your original foliation is, but we do know what the holonomy groupoid or algebroid or whatever of the linearized foliation is. So this is kind of a candidate for the, if there exists a Lie groupoid which gives you the original foliation, what we have constructed is a candidate for its linearization.
Right.
So I mean, it's like you don't know what the holonomy in the regular case. It's like you might have a foliation which you don't really understand what's going on for the foliation, but you do understand what's going on for the version, like if you linearize it and look at the bot connection. So that's what we're doing, right? So this is, but we can reformulate your question just about linear foliations, right?
Right.
And then it is true that this algebroid or this groupoid, the groupoid which integrates this algebroid, is controlling the geometry of the quotient space. And it's like the best way to control the geometry of this quotient space is, I mean, what is this quotient space, right? So I would argue with you that the quotient space is the stack represented by the holonomy groupoid of, well, the groupoid which integrates this algebroid. And that is the quotient space.
Right. So in that sense, I can see a kind of program, like a dream, like a letter to Santa Claus in a way, right? I don't know how plausible this is, but can we produce, suppose I want to produce manifolds with or Riemannian manifolds with a given holonomy group, right?
Mm-hmm.
Then, but I want them to be singular. Suppose I want to construct, producing manifolds with prescribed holonomy is in some sense dealt
Yeah.
with. But we don't have a singular Berger's list, right? So you could, I mean, it's just as reasonable to ask,
Sure.
Berger, right?
I mean, I would put
Which
that in
holonomy groups can be the groups of sufficiently simple manifolds with conical singularity, right? So
Sure.
we should be able to prescribe a certain singularity profile, and then each of these prescriptions generates a Berger's program all over again. And then what I'd like to do is use your technology to say, I don't know, manifold with holonomy, whatever, which is singular, emerges as the leaf space of maybe not so of a singular foliation some dimensions higher, right?
Uh-huh. Yeah, I think that would be very nice. I would start with orbifolds and
Right. Yeah. Just start with
right, I
orbifolds.
mean,
Start with anything which you already know are leaf spaces of things.
yeah, and then but you see, there is a, like, if you want to apply what I just said to this program, which would be very nice, you would have a problem, which is we construct things in which we know that the holonomy group is, I mean, is inside, is a subgroup of some group, right? I mean, you don't really
Right.
have control. I mean, you don't have control of what the holonomy group itself is, right? I mean, you see, it's like if you look at, so I'm just thinking out loud here, right? So if
Yeah.
you look at, say, like Bryant's original paper on existence of metrics with exceptional holonomy, with holonomy
Yeah.
G2.
Yeah.
So one of the hardest parts is to actually prove that the holonomy group is not just a subgroup of G2. It's actually surjective. It's the full group, right?
Yeah.
And you could do things. You could use this. I guess you could, like, with, I'm dreaming here, but I guess you could use this kind of technology to try to produce things which have holonomy inside a specified group.
I'd be very happy with that. Contained in is
Contained in.
already pretty great. I don't
Yeah.
think you can use your technology to prove
I
that
don't
it's
think so.
equal.
Yeah.
You'd have to look at coverings and stuff, which might relate to what to do, but it has a different flavor, right? It's these
Yeah.
Shiga,
Yeah. I think
Gromov,
so too.
factorization theorems and stuff. But
Sure.
at least contained in, right? Can I guarantee that the leaf space has holonomy contained in a certain group? It looks like you have the
Yeah,
technology
I
in
think you
hand
can.
to
Yeah,
sort of
I think
try
you
and
can do something
ascertain
like
this.
that. Yeah, you can do
Cool.
something like that. I guess.
Cool.
I mean, it really depends on how you define the geometry on this singular space, right? But yeah, sure.
Yeah.
I mean, that's the first step, right? I mean, of course, if your singular space is an orbifold, then you have a very good definition of what the geometry is there already to use. But if your singular space is weirder, then I don't know. But yeah, I guess.
I'm not being very demanding there. Just any systematic way to think about this, even for known cases, I think would be interesting.
Yeah, I think so
Uh,
too. I think that would
because
be very nice.
from your perspective, it doesn't really matter if it's singular or not. But if you start right, you just think of it systematically. Then if it's singular or not, it's kind of a peculiarity of your
Sure.
groupoid, algebroid thing at the other side of the mirror. But from a Riemannian perspective, then it does matter quite a bit if it's singular or not, right? You basically have to redefine everything, and in your case, you just have your language is kind of indifferent as to whether So it seems to me that you're in a better position to talk about things which are strictly Riemannian geometry people are unable to put into words. It's a first step for a cure.
Yeah, that would be nice.
Perhaps second question is, so you get this bot connection, right? Which is in some sense transversely flat, right?
Yeah.
Or rather not, right? It's flat along the fibers and transversely not flat. I suppose it's this. Yeah,
So
yeah, it has to be. It has to be because it's the connection that makes your holonomy independent, sort of homotopy in there. So yeah, it's kind of flat
sure.
along the fibers, but it's not flat on the total tangent bundle. It's flat along the fibers, right?
Yeah, it's flat. Well, I mean, it's only a connection on the normal bundle, but yeah, sure.
Yeah, but surely you can extend it to a connection on the whole
Sure,
manifold, I suppose.
in many ways, but yeah, sure.
Right. So to every connection, you can associate an energy, which is like it's Yang-Mills energy.
Sure.
So your thing is transversely flat, but precisely the ways in which you extend it are not flat on the whole manifold.
Yeah.
So in some sense, there should be a best one. There should be a best way to extend your thing, right? Which is sort of normally
Like
flat.
a critical point of the Yang-Mills
Precisely.
functional.
Precisely. There should be a sort of instant-on way, which then hopefully would be unique. And if it's not unique, that's even more interesting if the critical set is degenerate. But it sounds like a concrete question you can ask. Just write the first variation of any one form you can add to your bot connection to make it into a connection on the full tangent bundle. There should be a couple of preferred ones. A
Sure.
handful of
I
preferred
guess, yeah.
Well, that sounds like something I would,
That sounds something like nice to look at, yeah.
yeah, yeah. Cool. So I had these two questions. Okay, we've got Marcos in line. Can you take another question, Ivan?
Sure,
Five
sure.
more minutes.
It's
Okay, go ahead,
it's not
Marcos.
kind of a sort of questions, but maybe remarks concerning the discussion with Enrique. So, in my humble opinion, if you're trying to imagine the natural three ways of this local model, the first one is it has helping to construct an equivariant cohomology. What Francisco Caramelo is doing right now, based on our survey about killing foliations and things like that. So the semilocal model helps a lot to understand what should be an equivariant cohomology for this kind of theory. And this is the best way we have to deal with the entire topology of the space M. Right now, I can see any other better way. But if you are just trying to think about a fiber bundle with a foliation, so if you can try things like Alan corners. So you can actually try to derive along the leaves. So you have then a theory of operators. So you have a regular foliation on this manifold B, the basis of your fiber bundle. Now you have a singular foliation on E, but then you can talk about Dirac operators deriving the directions of the fibers. This is a kind of approach. And you can, in this set, you can think about Ivan told us you actually don't have much control about the holonomy foliation. The picture you have is you have a subfoliation, some kind of holonomy foliation that is just a translation inside of the linearized foliation that is in some sense the bigger homogeneous foliations, and this is actually the linearized foliation is what describes the entire symmetry of the foliation. So we have these subfoliations there, and this is not intrinsic. So you can actually ask about the holonomy foliation that is inside of this linearized foliation if you have someone with less curvature. So it's quite natural in this set to make something like Yang-Mills. So you try to minimize the energy associated to this holonomy connection, because you have a lot of possibilities of the holonomy connections contained in this singular foliation of A. And according to the answer, if you, for example, if a very simple case, if you achieve that among this class you do have a flat connection, inside of the holonomy, or a flat holonomy connection inside of your foliation, then you can, for example, get a IAMAB problem with constant scalar curvature that preserve the distance of the leaves. This is a kind of direct applications why I care about flat connections inside of these foliations on the fiber bundle. For example, if you find a flat, then you get almost immediately a metric with the constant scalar curvature, so that the foliation, with this respect to this new metric, the foliations are still Riemannian. So, and it's a very simple problem of Yamabe because you reduce dimensions, so you don't have to deal with the critical coefficients of Sobolev immersion. So this is a kind of program when you are dealing just with foliations in fiber bundle. Then you kind of start to think about operators along the leaves, not in the direction of Richardson, but in the directions more of Alan Cones. That means you derive along the leaves, as should be in the direct theory. So this is the second way. So the first natural direction is equivariant cohomology. The second natural way is to restrict the attention to foliations on fiber bundles or vector bundles, but then try to make a theory of operators. And questions like, can I have a lower holonomy connections so that I can get better metrics there? This is okay. This is this seems to work. There is some partial results in that directions. And there is a third direction that works, but then there is nothing to do with analysis, less with the partial differential equations, more with the dynamic. So if you have, for example, mean curvature flow or some geometric flow that is invariant, so you can use a semilocal models to control this base of attractions. And in this case, the models work quite well because the model, as Ivan explained to us, is an approximation. This approximation holds all for the connections. If you have the Riemannian connections and the Sazak connections, and the, for example, bounded geometry assumptions, they are close to each other. So you can use the semilocal models to control, for example, mean curvature flow under bounded curvature conditions, bounded geometry. This is a paper that I have with Leo and Icaro, for example, illustrating this idea that you control the relations between the Sazak connections and the Riemannian connections. So essentially there is in my humble opinion, three natural applications of the semilocal model. One is to formalize things about equivariant cohomology. Another is restrict attentions to foliations on vector bundle, but then you can try to do some partial differential equations and operator theory. Leo, Marcelo, and I, we are writing a very small note about in these directions called the Palais principal symmetry, just to illustrate how partial equation, how this groupoid structure that Ivan told us can be very useful, because if you have a groupoid, you have an average operator. And this average way to make integrations over the source of this groupoid helps a lot. There's a kind of operator that make basic functions, and so you can just generalize something called the Palais principal symmetry that allow to simplify some problems of partial differential equations. So this is a small paper that we are writing just to illustrate the second directions, to study foliations on fiber bundles, and that this structure can somehow help partial differential equations and should help operators at some point. And that is the third way is to control more the dynamical behavior. This is nice, but then you don't use directly one solution of partial differential equation to the other. You start to control the difference between the Sazak connections and the Riemannian connections. It is a different approach, but I don't know. I like these three approaches. I don't know if I helped the discussion with Ivan or I make everything confused. Ivan, what do you think about? Sorry.
Well, maybe I can encourage you to tell us more about it on your own talk which will be in October.
Okay. I can give a very naive talk about this how to partial differential equations, fiber bundles, and use this nice structure of the groupoid to make an average. And this average operator helps to understand the symmetry of some partial differential equations.
All right.
This is,
so more about it in 1 month's time.
Okay. I think we can give a talk. And I would like to show that also to Ivan, because we have some natural questions how to cite this properly. Because as Ivan can imagine, I started everything with the coordinate. And everyone is very angry with me right now because I make integrations with the coordinates. So everyone is very angry. But the idea is it's nice. The idea is nice. So sorry to disturb. I was just... but anyway, if I will meet you in 1 week. If you are in USP, I will try to find you next Friday.
Great.
Great. And we're looking forward to your title and abstract for your talk on October the 7th, where we can take this conversation further. If there are no more comments,
thank you, Ivan.
then
thank you very much for this.
And let's thank Ivan again. Yeah.
Thank you.
Let's thank the speaker again. And we'll see each other in 2 weeks' time for Mario Garcia Fernandez telling us about